afternoon, I'm Mosier Locke, and this is Axel Reed. We're here representing the Oregon Tech Geomatics program, along with our advisor, Mitch Duryea. We want to give a shout out to some of our team members that couldn't make it here today. They didn't want to come to DC and do a sweet presentation, but they helped a lot with the field work and setting up the technical report and binder, so thanks to them. The purpose of this project was to establish a vertical control network inside of Boyman Hall on the Oregon Tech campus. We wanted to set it up for future monitoring of potential vertical displacement. Utilizing information found in the NOAA Geodetic Leveling Manual, paired with high-precision equipment, our team established 41 benchmarks in and around Boyman Hall. Several level loops were formed with many redundant observations, starting at our benchmark Ager, or NGS benchmark Ager. This data, the data collected was then processed in a StarNet software using a least squares adjustment. The adjustment of the data resulted in a worst case 95% confidence interval of 0.631 millimeters for the benchmark elevations. If a similar process is followed for future observations, vertical displacement of greater than this magnitude will be detected. This will enable the Oregon Tech Facilities Department to monitor the building for any vertical shift.
High-precision vertical control networks are established for a number of reasons, including deformation monitoring of existing buildings. For this project, we chose to set a control network in Boyman Hall, a building on the Oregon Tech campus which holds classrooms and labs. Boyman Hall, the southwesternmost building on campus right there, was originally intended to be an addition to the existing Seaman Hall just to the north of it, but was actually built and designed as a separate building in 1974. It was built on a small hill that required some cut and some fill material. There has also been visible floor cracking and misaligned doors and walls. The basement of the building also has a smaller footprint than the ground floor, as shown in this cross-section. You can also see the area of cut over here and the area of fill material and the approximate original ground location. These factors all combined to make a less than stable ground subsurface, especially on the west side of the building. In this video, you can see the existing Seaman Hall, and this is the northern wall of Boyman Hall, and the western wall. And here you can see the slope, which goes down to the existing soccer field. Here you can see some cracks in the concrete in front of Boyman Hall. The cracks in the hallways inside of Boyman Hall are no longer visible because the tile has since been replaced. Klamath Falls is also located in an area which is prone to earthquakes. It is located at the northwestern corner of the Basin and Range province, which has north and northwest trending normal fault lines. Because of this, shallow crustal earthquakes do pose a risk. On September 20th of 1993, two such earthquakes occurred. One of 5.9 on the Richter scale and the other at 6.0, followed by over 3,000 lower intensity events over the course of the next 5 months. Two buildings on campus developed large cracks in brick walls. While not a whole lot of other damage was done to campus, the earthquake did prompt the school to have a structural study conducted of Boyman Hall. Braun Intertech was hired in 1994 to conduct this structural study. They found that settlement of fill material had caused cracking in the floor and the misaligned doors and walls. Their recommendations included removing the existing floor and slab, replacing and recompacting fill material, adding crushed base rock for leveling, and installing a new floor with joint control spacing. However, this work has been postponed so as to not disrupt students and faculty. Boyman Hall continues to settle, so our team, with some help from the facilities department, established the vertical control network to monitor this settlement. Also, if another large earthquake happens in the future, this will be a useful tool to monitor any effects. The team had three main goals in designing and implementing this vertical control network. Number one, to design and install a vertical control network in Boyman Hall. Number two, to perform the leveling to establish a baseline vertical control network to monitor future building deformation. And number 3, to develop a system for the future collection, storage, management, and application of vertical elevation data from the vertical control network.
To find typical industry standards for structural deformation, Dr. C.J. Riley, a professional engineer, was consulted. Dr. Riley is a professor of structural engineering at Oregon Tech in the Civil Engineering Department. In an interview with Dr. Riley, he recommended locations for benchmarks in and around Boyden Hall's load-bearing features. Dr. Riley indicated that he would like to see an accuracy of 8 millimeters or less for each benchmark elevation. The first step in setting up the vertical control network was choosing locations for benchmarks. The team consulted with the Oregon Tech Facilities Department to select locations that they were particularly interested in monitoring, also ensuring that there was a line of sight between each benchmark. Since these benchmarks would become a permanent feature of the public high-traffic building, they were placed in inconspicuous, low-impact locations. The team carefully chose materials and an installation method designed so that the benchmarks would remain fixed. 1/4-inch carriage bolts, 1 inch in length, were selected for the benchmarks. You can see an example of one there. These were chosen because their low-profile rounded heads provide a high-point surface for the end of our rod to be set on, while also reducing the risk of a trip hazard. The stainless steel material also prevents corrosion. The shoulders of the carriage bolts were removed, as you can see, by a grinding machine so that the bolt heads could be placed flush with the floor. The team set carriage bolts at the base of 12 columns outside of Boyden Hall and placed 29 more on the interior of the building. Most of the points are located on the west side of the building. That's because that's where all of the cracking and misaligned door jambs were seen. You can see, like on the poster over there, that they're primarily on the west 2/3, or the west side mostly. Holes were drilled with an 18-volt cordless impact drill using a 5/16" masonry bit. That's 1/16 of an inch larger than the shaft of the carriage bolts. The first step in setting up, because of an asbestos risk, several of the holes in the offices were pre-drilled by facilities staff. In order for the bolts to have a clean surface to adhere to, we used a squeeze bolt to remove any residual concrete dust. That's the squeeze bolt we used right there. After the dust was removed and the surface of the holes was wiped clean, the bolts had a thin layer of epoxy applied to them, and then they were inserted into the holes. The threads along the shaft of the bolts provided a good rough surface for the epoxy to cling to. The epoxy chosen is strong, durable, waterproof, and clear so that the benchmarks will remain fixed and the appearance unnoticeable.
The equipment our team used for the observations include a Wild NA3000 digital level as shown here, a digital in-bar rod, a tripod, foot coasters and support chain to keep the tripod feet from contacting the floor and also to keep the instrument stable, an LED flashlight to illuminate the digital in-bar rod scale, a hammer to set turning spikes in the ground outside the building, and a turtle, as shown here, for turning points on hard flat surfaces inside the building. In order to establish high precision elevations for each benchmark, we ran one level circuit and several level lines. Before beginning the level circuit, we performed a standard digital instrument peg test on relatively flat ground outside of the building. The first level circuit started to the northeast of Boyden Hall up here at Ager, which is a Class 2 NGS benchmark. This circuit then ran counterclockwise around the building, taking observations at each one of the exterior columns, and where possible, taking intermediate foresight observations inside of the building into the hallways here, 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 and here. The circuit then closed back on Ager. This circuit set up benchmarks to connect to the inside level lines. Here you can see some of the team taking observations on one of the exterior columns inside of the hallway here and on benchmark Ager. Two main level lines were ran through the north-south running hallways inside Boyden Hall here and here, and connected to the exterior columns here, 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 and here. The first started on point 3 and ran south through the hallway, closing out on point 3D, taking intermediate foresight observations along the way. The second one, similar to the first, started here at point 2 and ran south through this hallway, closing out on point 2D, again taking intermediate foresight observations. One more line was ran connecting the western hallway to a hallway that runs through faculty offices here. We also included additional setups to incorporate the shorter hallways that run east-west here, here, and here. The lines incorporated all benchmarks and maximized redundancy. This greatly strengthens the network by decreasing standard errors in computed elevations and increasing our ability to detect blunders and unmodeled systematic errors. Here you can see the team set up inside of Boyman Hall, taking observations in the western hallway.
Due to the age of the instrument, field notes had to be recorded manually because the data collector could not be plugged in. Field notes were recorded in a standard rate in the range field book. The crew member operating the automatic level would call out 3 digits at a time, and the note taker would repeat those 3 digits to ensure that they had been communicated correctly. Each rod reading was recorded to 1/100,000th of a meter. While one crew member was creating a hard copy of the notes, another was inputting the values into a computer spreadsheet so that we could have a hard copy and a physical copy, or a physical copy and a digital record. The notes for a given setup consist of a backsite of the previous benchmark, any intermediate foresights, so as to get redundancy, and foresight readings on the next benchmark. There are several methods available to surveyors to mathematically account for and adjust random errors in measurements. The least squares adjustment method was applied to the precise leveling of Boyman Hall. This method adjusts for random errors of instrumentation, errors which follow the laws of probability and follow a normal distribution. Generally, the errors are expected to be small, with both positive and negative values occurring with equal frequency. Least squares also gives the surveyor a way to detect observations where a blunder may have occurred. The additional benefits of least squares is the statistical data provided. Using statistical reports from StarNet software allows for a determination of the confidence interval, which tells the reliability of computed elevations. These observations are redundant and recorded by completing a level circuit. 3 lines were completed, 1 down each hallway and 1 to connect the hallways. The redundant observations tie the lines together and strengthen the survey network. In addition to generating precise elevations for the control points, a visual depiction of the elevation of the floor is necessary. To estimate XY positions for the control points, team members tape 2 distances from building or from wall corners and door frames that are identifiable on a CAD drawing of the Boyman Hall floor plan. By finding intersections of these distances, we were able to determine horizontal positions for the benchmarks in relation to the floor plan. ESRI's ArcMap software was used to georeference the floor plan of an existing shapefile to the Boyman Hall and generate real-world XY position coordinates for each control point. The points were stored with their position data in a GIS feature class inside of a personal geodatabase. Personal geodatabases can be modified using Microsoft Access, allowing future elevation data to be easily added using Access to update the geodatabase, keeping all data in one location and simplifying the process of computing elevation data gathered at different epochs. To visually depict the differences between the benchmarks, the elevation values were interpolated using a spline technique to generate an elevation surface. This interpolation is estimating the elevation of the floor between the benchmarks of Boyman Hall, but is a powerful visualization tool. It serves to identify at a glance where the high and low points of the building may be. By looking on either side here at the maps, you can see that the red indicates the high points of the building, where the dark green indicates the lowest parts. The benchmarks on the exterior columns distort the interpolated elevation on the edges because of their placement. Most of the benchmarks on the column are placed on where the column kind of slopes up and down. So the benchmarks may be placed higher or lower, which is maybe what's causing the distortion around the edges. A 3-dimensional rendering of the same interpolated surface was generated in ArcScene, which more strikingly demonstrates the elevation differences. The 3D image is interpolated surface based on benchmark elevations. The purpose of establishing these surface renderings was to provide a baseline with which future surfaces could be visually compared. As future elevation data is gathered, generating similar surface models and comparing them to the baseline models will help to identify patterns of change in the floor.
To give a little perspective before getting into the results, a dime is about 1 millimeter thick, and a micron is 1/1000th of a millimeter. So the standard error of a rod reading was 10 microns. This corresponds to the standard error of the elevation difference between the backside and the foresight of 14.1 microns. Station Ager, a Class 2 NGS benchmark, was used as the only constraint for this adjustment. There were 65 elevation differences observed between 41 benchmarks, 24 of which were redundant. The largest residual of the adjusted observations was found to be 1/4 of a millimeter, with only 3 observations coming in at over 2/10 of a millimeter. An error factor of 9/10 was found, well centered between the upper and lower bounds of the chi-squared test. The a posteriori reference variance confirms the instrument manual's standard error was reasonable. The largest 95% elevation confidence interval was found to be 2/3 of a millimeter. These results easily meet the specifications of 8 millimeters of accuracy. Going back to the perspective, our results show that these measurements would be able to detect the thickness of 2/3 of a dime if that were placed over one of the benchmarks. Here you can see our largest 95% confidence elevation interval here, and you can see our number of observations, unknowns, and redundant observations, and here you can see that we did pass the chi-squared test. Through this project, future monitoring of deformation at Boyden Hall was made possible. Prior to this project, the only evidence of any settlement was cracks in the floors and misaligned doors and walls. Future measurements will show if the shift is uniform or in relation to the exterior columns. These future measurements will be taken at Oregon Tech in introductory geomatics courses. They will show if building modifications are necessary. A magnitude of 3 millimeters would show monitoring is not necessary as often, while 8 millimeters would necessitate more frequent monitoring, and 15 millimeters would require urgent action. This project could also be used as a prototype for other buildings on campus. The team achieved exceptionally definitive results, but the project could possibly be improved by adding another NGS benchmark to the circuit. The team accomplished all of the goals we set. We successfully installed a vertical control network. We performed the level circuits while maximizing redundancy, and continued monitoring will be done by introductory geomatics classes at Oregon Tech. Plus, a geodatabase was created to store future results for comparison. The team has successfully developed a solution to an infrastructure challenge and improved campus community, but has also experienced firsthand all stages of a practical application of a high-precision vertical control network. Any questions?
Yeah, just a quick one on what part of your notebook you show the schematic of where you ran your levels around the outside of the building, and one of it's point B, I guess that's one of the benchmarks. You have A, B, C, D. With just a side tie, I'm just curious why that wasn't turned through.
I believe it was.
It was from point number setup number 4.
Setup number 4.
Yeah, on here it shows the sketch that I got.
Oh, yeah. That side of the building, because the slope is right next to the west side of the building, it's really hard to set up over there. So we were just able to do that as an intermediate foresight.
Yeah, it's always best if you have an independent check, so you don't have another setup, and then
Yeah.
even if you're just going to side tie. Thanks.
On your diagram there, the shading and things like that, does the shading represent what's subsiding or what's staying the same?
Right now, it doesn't indicate the same. It's merely just a depiction of how the elevation looks on the inside. We don't have data to say how it's changed. We're going to gather more data next fall, so we can say this is how it's changed, this is where it's moving, or where we think it's moving at this point. Right now, that just shows where the lowest elevation is for what we have and where the highest is.
Okay, relative to the green, I guess, is that, we talking 3 millimeters, 4 millimeters?
The difference between the lowest and the highest is 0.2 meters. Yep, 2 decimeters. So a pretty good amount.
Yeah.
And again, that's going off of, so the bottom left shows the highest elevation, and that could just be based off of where the benchmark was placed on the column, whereas the surrounding columns, it could have just been placed in a different point. We're mostly concerned with the benchmarks inside the building, because that's where we observe the majority of the cracking, the slant doors, and the most reliable data is inside there.
Seeing what looks like a lot of change inside the building, is it noticeable when you walk down the halls? It's not noticeable?
Just walking, not so much, but when they don't have, when we were able to see the cracks in the tiles, you could definitely see a slight crown going down the hall.
Sounds to me like your leveling was quite excellent, but I wonder if in working with any engineers or other facility services or anyone, is there an expectation of the likely subsidence rate in the building?
They don't know what the rate is, but they do expect the west side of the building to sink.
They don't, yeah, but they don't estimate any magnitude yet.
No, and the building was built in 74. The earthquakes were in 93. So a lot of time has gone by and it hasn't sunk enough to require them to replace anything other than the tiles.
Thank you.
So if you have another earthquake, you can go check it?
Yeah. Yes, exactly.
Looking between the image on the left and then the image on the bottom right, are the most, y'all said y'all were focusing on the top 2/3, right?
Just on the west.
On the
Mostly
west?
on the west, yeah.
Okay.
So all the points on the left side of the building are where we were focusing.
And does that match what y'all saw on the right page? I don't,
Look on the right side of
yeah.
the surface. Yeah, it matches fairly well. There's a lot less, there aren't any noticeable cracks that we've seen running through the halls, and a lot of the door jambs are still fairly well aligned. But it's very noticeable on the left side, on the west side, when you're walking through the hall and opening and closing doors.
So you talked about false impression in the southwest corner of your surface rendering there, because some of those benchmarks along the exterior are perhaps set higher because there was not some kind of a mechanism for making sure they were all located in a similar place. Is
Yeah.
that right?
So each one of those exterior columns has a slope on the bottom of it. And so if we set it just a little bit lower on that slope, it's going to make a difference. And then also each one of the columns it's like poured concrete with a material on top of it. And so even if they poured it a little differently, and so, I mean, there are a few different factors that could affect the exterior columns and where the benchmarks were placed.
So in the future, is there a way to try and control for that? Because obviously, it's showing that the southwest corner is quite a bit higher, right?
Yeah.
I mean, that 2 decimeters you talked about, a lot of that is possibly from, shall I call them errors or mistakes in the location of the benchmarks that give you a faulty impression of the surface.
So for what we did for this project, it was just setting a baseline. We just needed to know what the elevations are today, so that in the future, if they go back in and monitor it, then they'll be able to see any change. So, I mean, the benchmarks around the exterior columns, even though they are different and in different places, the main focus of this is going to be what happens with the floor inside. So, and then also what happens in the future.
So did you try to do a surface without the troublesome benchmarks to see what you got?
We didn't.
Okay. Thank you.
That's it for questions? I think we're done for questions. We'll catch them afterwards. Okay. And thank you very much.
Thank you.